Hello and welcome to Mind the Stats. My name is Mohammed Radisi and I'm here to talk about binomial distribution and its applications. My mission is simple: to take a difficult subject and break it into small sections to make it less of a challenge. I'll walk you through one or more examples to reinforce what you've learned. I'll welcome your feedback, questions, and suggestions. Please subscribe to my channel for future sessions or improvement, and thank you in advance. Before we get into the subject of binomial distribution, I would like to remind you of the two types of data we encounter in everyday life: the continuous and categorical data types. First, the continuous variables. They can be measured and quantified. They have unlimited subdivisions. They can be converted to different scales. For example, a distance can be expressed in kilometers, miles, or subunits like millimeters and inches. We can perform arithmetic operations on them and statistical operations on them. Applications are limitless, and here are some examples of continuous variables: temperature, pressure, height, length, time, etc. The second type is categorical variables. By categorical, we mean we intentionally subdivide our data into groups. We do this depending on a specific quality or quantity. The method we use to group the data is subjective, to satisfy a need for the study we're conducting. The most common categorical classification is binary. Some literature refer to binary data as attribute data. The binary attribute data are limited to two choices, such as yes or no, or good or bad, or on or off. The binary data is used in quality control, public opinion surveys, and medical research. In manufacturing, we use terms such as defective, non-conforming, or conforming, or non-defective. Categorical or binary data can be counted and proportioned. So an inspected unit either has or has not a predetermined quality. Say we're checking for dents or scratches on a part. The part is either clear of defects or has one or multiple defects. But in the binomial world, a part with one or more defects is called defective. This is extremely important. We briefly discussed the difference between the two types of variables. We've learned that we can count and study the proportions of binary data. But what about performing probability study on attribute data? That's where binomial distribution comes into play. If P is the steady state reject rate of a process, and X is the number of defects found in a sample size n, then using the binomial distribution we can find the probability of finding X defects in a sample size n when the reject rate of the process is equal to value P. So you can imagine how useful this could be. In order to use the binomial distribution, we have to meet certain conditions listed here. The number of trials is fixed. Each trial is independent of the other trial. Since we're dealing with binary outcomes, each trial falls in one of the two categories. The probability of an event is the same for each trial. Let's say, since, for example, if we throw a dice, every one of the 6 faces have the same chance of coming facing upward. That's what that means. The binomial distribution has a skewed shape, similar to the blue one on the left here in that chart. This happened to be for a sample size of 30. As the sample size increases, the shape of the distribution starts looking more and more like a normal bell curve. In this example, the red distribution is for a sample size of 300 compared to the blue one for a sample size of 30. So let's try to apply the little bit that we've learned through a simple example before we dig deeper into the subject of binomial distribution. The production manager of a donut factory was curious to note that his reject rate at a glazed donut line has jumped from the usual 5% to 17%. He did this by selecting 30 glazed donuts at the end of the line and found 5 of them not to meet the quality control guidelines. So he wondered if this is a coincidence or an indication of something significant with the production line. So his question is, what is the probability of finding exactly 5 rejects from a sample of 30 when the production process runs at a steady state reject rate of 5%? So we're going to go through step by step of how we can get an answer to his question. So throughout the session we'll use Minitab, but any other statistics package will produce the same result. When you first start Minitab, you get a blank screen with a session window where you get your output and a worksheet where you can either place your inputs or receive some outputs in columns or cells. You also get a list of commands up here. The command we're going to be using is calculate. We're going to scroll down to probability distributions and we're going to select the binomial. For us here we have 3 choices, but we're going to pick the probability because that's what we're interested in. The number of trials or the sample size is 30. The event probability is 5% or 0.05. And we wanted to find for the probability for a single value, which is 5. We click on OK. And Minitab displays and X is 5. And the probability is 0.0123 and change. And here's a summary slide. We're interested in finding the probability of finding 5 defects in a sample size of 30 with a reject rate of 5%. We went to the command in Minitab calc. We selected probability distribution, binomial, and we selected the first option, which is the probability. We entered 30 and the number of trials, 5% in the event probability, and we wanted to find the probability of finding exactly 5. We clicked OK, and we, in the session window, we got the response, which is probability of 0.0123, which is essentially over 1% chance of finding exactly 5 rejects. You may have heard of density functions when you've studied histograms in the past. In histograms, we take a list of values and bin them and show the frequency of each bin value. Like continuous data, discrete events can also be represented by histograms of frequencies. You can see that in the histogram that is shown in the bottom of your screen, where the y-axis is the frequency and the x-axis is the different events or event values. A probabilistic model that approximates the behavior of this histogram is known as the probability density function, or PDF for short. So in PDF, the y-axis is replaced by the probability of density, a probability or density, and the x-axis is the different events. in binomial distribution, PDF is used to determine the probability of an exact value or exact data value given a sampling size and a steady state performance rate. Like histograms, PDF indicates regions of higher and lower probability. This is the area of higher probability, and the tail ends are the areas of lower probability. We're just going to say a few words about cumulative and inverse cumulative density functions. As the name suggests, cumulative distribution function determines the cumulative probability of each of values between given limits or less than or equal to a certain values. And the inverse cumulative distribution function is essentially the inverse of it. So it gives the value of the variable associated with a specific cumulative probability. We'll get to use these in the next slides and also in future sessions. I think you should know by now that the binomial analysis can be used to calculate the probability of finding exactly X number of events in a number of trials of size n when the probability of failure is known to be equal to P. The formula looks like this with factorial on the numerator and denominator. A special simple form of it is when x is equal to 0. It really, a lot of these factors simplify themselves to 1, and then you end up with 1 minus p to the power of n when x is equal to 0. The value p, or the reject rate, if it's not known, it can be estimated as a number of defective units by the sample size you choose over a period of time when the process is in stable condition. Such approximation could be qualified using a standard error, but we're not going to discuss that in this session. Earlier we found the probability of finding exactly 5 rejects. But what if the production manager asked you what is the probability of finding 3, or finding 2, or finding 12? So it may be a good idea to give them a list of what are the probabilities of getting different values, and that's what we're going to see next. So this is how we're going to be able to find different probabilities, or probabilities for different values of x. I'm going to go to the worksheet, click here, and I'm going to call this x. And I'm going to start for 0, 1, and then I'll show you a trick. I can select these 2 rows and go to the corner here where the cursor changes shape and drag it down to, let's say, 20, 21. Okay, so we're going to calculate probability for all these events, and we're going to put the result probability of x, or f of x, whatever you want to call it. Then we'll go up to the same command, calc, probability distributions, binomial, probability, 30, 5 for the trial, 5% reject rate, and in here, instead of one constant, we're going to say input column, and we're going to click in there, and as you can see, the column we have available for us is C1. I'll double click on it, and the storage, we want to use this guy, and there it is. It calculated for all the values of x we listed in column X. So here's a summary sheet. We can extend this, like we said, to any value of X for the same parameters, a sample 30 and reject rate of 5%. We issued the same command, calc. We select the probability distribution to be binomial, and we entered, instead of a constant, we entered for the input column the different events we wanted to calculate probabilities for, and where the output is going to be displayed in the spreadsheet or the worksheet. We clicked OK, and voila, this is what we get. So as an example, to find exactly one reject in a sample of 30 at that rate, it comes down to like 0.338 or 33.8 chance, but the probability of finding more gets lower and lower. And to go back to our initial example earlier, to find exactly 5, it comes down to about 1% chance. Next, we're going to show you how you can visualize the data. A lot of people prefer graphs, so we're going to show you how you can do that. So here's our screen from the last session, Minitab session. We go to graph, we select the bar chart down here, and we tell it the data is in a table, and we double click on the simple type of chart. In the variable for the graph is f of x, and the category variable is x. We click OK, and we get the chart. Now if you plot the maximum of each one of these bars, you can see the skewed distribution, which is a signature shape of the binomial distribution. And here's a summary slide. We selected graph from the list of menus. We selected bar chart, and from the pull-down menu, selected values from a table. We selected one column of values and entered the information, the values that we wanted to display in the graph variables, and for the x-axis we used x as a category variable, and we clicked OK, and we got this chart. Earlier we touched briefly on cumulative probability, and here's when we could use it. We're often interested in the probability of observing no more than x defective units. So rather than exactly x defective units, we want to find out if it's x or x minus 1, x minus 2, x minus 3, etc., etc. So up to that value, and this is how you can do it. So this is our session from before. I'm going to minimize this chart. I'm not going to delete it, but I'm just going to minimize it. And right now we're interested in the cumulative probability. So I'm going to click right here, and I'm going to say cumulative p probability of x. So that's where my output is going to be. Again, we go to our command calc, probability distributions, binomial, and then instead of calculating probability, we're going to calculate the cumulative probability. These don't change. Our input is the same, but our output, we want it to be cumulative. So I'm going to double click after highlighting what's in this field. I'm going to double click on that and click OK. And that is the cumulative probability of finding 0 defects, up to 2, up to 3, up to 4, etc., etc. And again, here's a summary slide. We're often interested in the probability of observing no more than some number of defective units, rather than exactly a number of defective units. For this, we performed the Minitab command, calc, probability distribution. We selected binomial. But instead of selecting probability this time, we asked for cumulative probability, because that's what we're interested in. Again, these didn't change, number of trials and reject rate, and for the input column X, and then we decided to put the data in a column called cumulative f of x, or whatever you called it. We pressed OK, and it output the cumulative distribution. Now you can chart it the same way using a bar graph, and you end up with something that looks like this. This concludes our session on binomial distribution. This also happened to be my first presentation, and I'm planning on putting out more on other statistical and math questions. If you happen to learn a thing or two from this, then please like my video, and better yet, subscribe to my channel for future releases. Please let your classmates and colleagues know about it, and thank you, and I'll see you on my next session.